from his side. And so we will going to talk about port-Hamiltonian modeling in quantum mechanics. So please, the stage is yours.
Thank you very much. Hello, I'm a master student at Isaïe Superior in France. And during my research track there, I worked with Ghislain and Denis Matignon on the Schrödinger Equation as a port-Hamiltonian system. And I'm happy to be here to present you some results. So, what's the ports in port-Hamiltonian system? So, I will first introduce the underlying structure, which are direct structures, and then we will model the Schrödinger equation as a port-Hamiltonian system. Thanks to this model, we will discretize the model, preserving the structure of port-Hamiltonian systems, and we will manage to make some numerical experiments with this. So the Hamiltonian systems connect the evolution of the state with time with the variation of the Hamiltonian in the, along the trajectory in the phase space. And thanks to this, you can write the Hamiltonian balance, this is the bottom line, as the inner product between the variation of the state with time, which is a kind of generalized velocity, with the gradient of the Hamiltonian, which is a kind of force. But is there a proper way to describe this balance, to take into account friction, interaction? So this is the role of direct structures. So which consists in pairing flows and ports, which are flows and efforts, which are the ports. So you have to rewrite the dynamics this way, using the matrix J, which describe the conservative laws, which is very useful in physics. You can add also, so this matrix is Q-symmetric. You have the arm matrix to model resistive processes, dissipation, and you can also take into account interactions with other systems through a control U and an observation port Y. So it's very useful to couple different systems to make them interact and to control them. So don't look too deeply into this slide. It's just to show you that it's a very active area of research. It has been applied to finite dimensional systems, but also to distributed systems, for which you can also apply a control and observation at the boundary of the system. So it has been applied in many fields: thermodynamics, mechanics, electromagnetism, but not in quantum mechanics yet. So what do we have to do? We have to define our system, how to control it, to introduce a proper Hamiltonian and the ports. So we will focus on the PDE form of the Schrödinger equation satisfied by the wave function. And we make the control appearing in the potential. So we split the potential into a stationary part and a potential of control. And from this, we can write the stationary part of the Hamiltonian. Using this, we suggest two possible Hamiltonians. The first one is based on the probability of presence, and the second one on the energy. And we can interpret these two Hamiltonians as the mean value of the operator identity and HS. And it's the equation of evolution is given by the Ehrenfest theorem, which is similar to the equations we have for Hamiltonian dynamics. And also we can rewrite in both cases the Hamiltonian as the norm squared of the wave function. So now the main problem is how to compute the variation of the Hamiltonian along the trajectories. So to do so, to define our functional derivative with respect to the wave function, we based our definition on the CR calculus, as you can see on the bottom line, and we identify the wave function to be the functional derivative of the Hamiltonian with respect to the wave function here. So this leads to these port-Hamiltonian models, which respect the complex Stokes-Dirac structure introduced very recently by Bernoulli. You have the skew symmetric operator J. You can see that whatever the control, you have the wave function as an output, which is very useful because you have all the information of the system as the output. And to recover the Schrödinger equation, you use this control, which is in fact a feedback, a state feedback of the wave function with the potential of control. And so using this structure, we get this Hamiltonian balance at the bottom line, so the balance between the two interaction ports, U and Y. But the wave function extends to infinity, and we would like to simulate the evolution of the wave function. So we have to define a model to simulate the wave function on the bounded domain. So to do so, we create a kind of virtual system using the restriction of the two previous inner products to the bounded domain. And using that, you also have in the Hamiltonian balance the current of probability which appears that we can interpret as the pairing between the wave function at the boundary and the normal speed. So we have two new ports at the boundary. So to sum up a little bit, we model our quantum system as a port-Hamiltonian system of stationary potential, but with a state feedback to recover the Schrödinger equation with the control. And for simulation, we created a virtual system, a port-Hamiltonian system, for which we introduce new ports due to the probability current. So now that we have this interesting structure, is there a way to preserve the structure of port-Hamiltonian system in the discrete level? So yes, and this is the Partitioned Finite Element Method, so which consists in writing your dynamics, your equation in the weak form, and then to integrate by parts to let the control appear. So as you can see, when we integrate by parts, we get the normal velocity control appearing naturally, but we would like to mix Newman control with Dirichlet conditions. So to make the Dirichlet conditions, we use Lagrange multipliers, and we introduce an algebraic constraint to the system. So we discretize our wave function on the finite real approximation space, and so we go from a distributed wave function into a vector, 1D vector, evolving on time, which is here underlined psi. And we get this big Dirac structure, a complex Dirac structure, and the main matrix is skew symmetric, which leads to this Hamiltonian balance where you have the pairing between the control and the observation ports. So we can sum up this structure preserving method. You go from a distributed wave function into a vector depending on time. You go from a Stokes-Dirac structure into which describe your PDE into a Dirac structure which describes your ODE with an algebraic constraint. And you also preserve the conservation of probability. These are the two bottom lines at the discrete level. So we can apply it to simple numerical experiments. Here we model a one-dimensional quantum box. So we apply homogeneous Dirichlet condition in all the boundary. and there's no control first. So the stationary states are well known and analytically known, and these are oscillating modes. And for the following simulation, we use Lagrange finite elements of order 1 for the space discretization, and we integrate the resulting differential algebraic equation with a MATLAB time integrator. So first, to check our implementation, we just simulate the stationary mode. So you can see here on the bottom plots that you recover the evolution of the oscillating modes and the stationary aspects in the probability density. And in the table, the right column, you can see that you respect the Hamiltonian balance quite well with very few time steps. And we can go further by applying control. So here you apply electric field to a dipole, and you will produce oscillation between, if the state is initially in the state number 1, you will create oscillation between the level 1 and the level 2. These are Rabi oscillations, which are known analytically. And so you apply a control of period, the analytical period of Rabi oscillations. And as you can see, we managed to go from the level 1 into level 2. But when we switch on the control, we worsens the accuracy on the Hamiltonian. This is the left figures, because the integrator is not very well suited to port-Hamiltonian systems here. But as you can see on the right figure, so you go from level 1 to level 2 with the right Rabi oscillations, and you can see also small oscillations when you don't neglect the rotating wave approximations. So to conclude, we managed to model the PDE form of the Schrödinger equation as a port-Hamiltonian system by introducing a state feedback. We applied a structure-preserving discretization method which preserved the probability balance. And we showed that we can apply very simple controls on quantum states. And during this work, we also extended the port-Hamiltonian modeling to complex states. So, but the main challenges is to model now interacting quantum systems, because the space of the states of interacting subsystem is the tensor product of the interval space of states. And port-Hamiltonian is made to connect subsystems to model complex systems, but it's the transformation only couples systems and by concatenating the states. So we need to find a way to apply to quantum mechanics interacting systems. So it requires further development on port-Hamiltonian systems. Yeah, thank you very much. Do you have any questions?
So, is there any question from the public? So I have just one question. Were you able to recover all the boundary conditions from quantum mechanics? So you know that there are conditions that are non-local, pairing. So if you consider a manifold with a set with a boundary, in order to preserve unitarity, you don't have only local boundary condition. You are able to simulate and consider also this type of setting.
So in terms of unitarity, this is exactly the Hamiltonian. So normally you have to preserve it thanks to a certain method for port-Hamiltonian system. Here is not really the case. And the boundary conditions for the quantum box is just 0 on the wave function in the boundary. So we just apply this
But you can
condition.
consider also the more general
Yes.
boundary condition.
It's more complicated because you need transparent conditions, for example.
So, okay, so thank you.
Thank you.
So let's thank again the speaker.